I'm Brian Hoover. My co-authors here are Dave Taliaferro, who produced the Mathematica graphics, Dave Bowers and Dave Wellams from ATA, who provided laboratory data, and Coherence Model co-author Victor Gamez of AFRL. Bottom line up front, this is, to our knowledge, the first demonstration of a diffractive spectral BRDF verified against measured surface microstructure. We measure surface microstructure with an AFM. In this case, it is the microstructure of Epner diffuse gold. The gold surface plot is the coherence model solution for the near monostatic spectral BRDF of Epner diffuse gold from 800 to 1800 nanometer wavelength and 0 to 80 degree scattering angle based on AFM surface measurements. And the purple surface is the BRDF measurement by an AFRL white light scatterometer. As will be explained, this has yet to be optimized over the full spectral band. We're developing the coherence model incrementally by testing and verifying it against particular classes of surfaces at a time. Based on our modeling criteria, the radiometric measurement and verification processes are as important as the modeling itself. We do not yet concentrate on rendering as much as typical developments of computer graphics models, although most computer graphics models are not radiometrically accurate either. We believe we're the first to verify diffuse surface scattering using AFM surface measurements. Here's the case of Epner diffuse gold. The coherence model has been able to model this reflector pretty well, and we continue to use it as a development standard. This is a NIST traceable gold coating used to calibrate IR instrumentation. It is diffuse, but much less so than a Lambertian reflector, which is shown here as a dashed line for comparison. This result was published in Proceedings SPIE in 2007. We measured the surface with AFM, extracted the parameters for the coherence model, and achieved this fit to near monostatic laser BRDF measured independently by AFRL RDL. For this installment, these exact same AFM surface parameters are maintained and provide good fits to spectral BRDF measurements of this surface made at a completely independent AFRL RVS lab with a white light scatterometer. So what is the coherence model and what can it do? It is a BRDF model based on the diffraction theory of statistical surfaces, which is a subfield of coherence theory. In particular, the von Sittard-Zernike theorem is applied to scattered field ensembles and provides a model average intensity. The model does not compute speckle patterns, it goes straight to the observable average intensity. The coherence model is defined in terms of measurable surface parameters, obtained, for instance, with an AFM, which means that model fits to radiometric data can be verified against independent surface measurements. It is not yet polarized, so we compare it only to SS polarized radiometry, but we've done some rather unique cases with it, including preliminary verification with anisotropic textures and the wavelength scaling and diffuse illumination to be shown. All of the plots in this briefing are average intensity, which is related to the BRDF through the equation at the bottom. I will use the terms intensity and BRDF interchangeably, but importantly, intensity, unlike BRDF, goes to 0 at plus or minus 90 degree scattering angle. Now, we believe the coherence model can be implemented fast enough for applications to computer graphics, even interactive video. It is radiometrically realistic, which implies photorealism at a quantitative level. Initial game applications could depict laser beam reflections from robots, vehicles, or buildings with radiometric realism. Diffuse illumination is important for machine vision, and we will talk about that. For design, the image at the lower left is a photo of a diffuse gold integrating sphere. And we expect coherence model renderings to resemble the photo much more than do conventional computer graphics BRDF models like that used to render the ring here. The coherence model should be useful for rendering instruments and manufactured products with diffuse metallic finishes. And our most recent application area is space situational awareness. Many SSA applications have only unresolved or poorly resolved imagery. And trying to classify or identify space objects without images requires accurate radiometric models. Since the rest of the briefing focuses on Epner diffuse gold, here we show the coherence model tested and verified for another diffuse metal, a satellite titanium with anisotropic finish. The measured anisotropic BRDF is shown at the upper left. It is on a log scale, so when you look at this reflectance function in the lab, it almost appears as a bright band of light oriented normal to the surface striations. We used an anisotropic coherence model based on AFM surface parameters to predict reflectance along that band and achieved the fit shown at the lower right at 633 nanometer wavelength without optimization. That is, the model surface parameters used to achieve this fit are the exact average parameters extracted from the AFM data. There was no optimization of the extracted surface data. And at the lower left is the extrapolation of this result to broadband, as will be detailed and verified for diffuse gold. So based on the SSA mission, these are the modeling criteria. The model must describe diffuse reflectors, which implies a different domain than low scatter optical quality surfaces. The coherence model treats diffuse surfaces and also certain smooth surfaces, and may be numerically extendable to general smooth surfaces, but this briefing is limited to diffuse reflection. Diffraction certainly affects radiometry, and any model must account for it to be accurate over relevant ranges. Geometric microfacet models, which arise from the stationary phase approximation to diffraction theory, are simply not accurate for most diffuse reflectors. Considering both laser and solar illumination and comparing the two, accurate wavelength scaling is needed, and wavelength scaling can only be accurate with a diffractive model. The model must be expressed exclusively in terms of measurable parameters. That allows verification and provides a physical way to put error bars on model predictions. Error bars are a priority, although we haven't had the chance to implement them yet. Model solutions must be compared with measured data, otherwise it's only mathematics. Data comparisons guide model development and ensure a usable model. And from a technology perspective, the model needs to compute fast to an observable quantity. The coherence model computes directly the average scattered intensity. It does not compute speckle patterns. Individual speckle patterns are not observable. There are some interesting mathematical results relevant to solar and general diffuse illumination. To model solar reflection, the model must of course account for diffuse illumination and should be applicable to sources even more diffuse than the sun. Diffuse illumination is characterized by a narrow coherence function. The coherence model incorporates diffuse illumination naturally in that the reflected coherence function is the product of the coherence function that would result from laser or coherent illumination and the coherence function of the diffuse illumination. We treat the sun as a thermal disk following the treatment of Agrawal et al. Now, looking at a geometrical schematic of a thermal sphere source, you can almost surmise that the effect of diffuse illumination is to convolve the laser BRDF with the angular spectrum of the source, and that is almost correct. But the geometrical approximation breaks down at large scattering angles. In this notional convolution plot, suppose the green curve is a diffuse laser BRDF, and the blue pulse is the angular spectrum of a thermal disk source. The problem is that this convolution does not go to zero at 90 degrees and larger angles. This is where coherence theory corrects the geometrical approximation by specifying a non-geometrical convolution. This is the von Sittert-Zernike expression for average scattered intensity assumed by the coherence model. Now, previously we published analysis of the constraints imposed by coherence theory on the integrand of this equation. In particular, coherence theory requires that this cosine squared factor be outside the integral. Other scattering models, for instance Beckman and Hay-Torrance, keep this factor inside the integral, producing a radiance integrand that is not allowed by coherence theory. Now, under diffuse illumination, the coherence model says that the coherence function mu becomes the product of the coherence function under laser illumination and the coherence function of the diffuse illumination. Since this is a Fourier transform, this integral becomes the convolution of the laser BRDF with the source angular spectrum. But critically, the cosine squared factor is applied after the convolution, which ensures that the intensity still goes to 0 at 90-degree scattering angle. You get that physically accurate behavior from the constraint imposed by coherence theory. It is important to realize that 2D convolution is always required, even if the data to be modeled is one-dimensional, as is most measured data. The 2D convolution differs from a 1D convolution and affects any 1D slice of the full hemisphere BRDF. This implies that the model must always compute the full hemisphere BRDF in order to accurately model diffuse illumination. This is a flowchart of the non-geometrical convolution operation in Mathematica for a less diffuse reflector, showing the effect of broadening the source solid angle. The coherence model scales with wavelength per diffraction theory. Here's what the model predicts for the monostatic spectral BRDF of Ebner diffuse gold from 800 to 10 micron wavelength, 800 nanometers to 10 micron wavelength, for laser illumination on the left and then convolved with the solar disk on the right. Under solar illumination, it's only slightly broader at longer wavelengths with almost no difference at shorter wavelengths. The effect is small because the surface is inherently diffuse. The effect of diffuse illumination will be much more pronounced for less diffuse reflectors. Then the animation shows the monostatic spectral BRDF as the illumination gets even more diffuse. The laser and solar BRDFs are actually the first two frames of the animation. We tested the model against a thermal white light source provided by the AFRL RVSS snowball scatterometer, which features a regulated tungsten lamp and a spectrometer in the receiver. ATA built this instrument and worked with us to provide radiometric spectral BRDF data. The snowball spectral BRDF for Ebner diffuse gold is shown at the bottom. The scattering angle is into the page, and the spectrum at normal incidence is evident along the upper ridge of the surface plot. This data is usable all the way down over the absorption edge of gold to around 400 nanometers. Above that is the reflectivity curve for Ebner laser gold from the Ebner website, which goes to 100% from around 800 nanometer all the way out past 10 micron wavelength. This reflectivity is applied to coherence model solutions as a wavelength-dependent emittance factor. Since the current coherence model assumes a perfect conductor, we didn't expect good fits below about 800 nanometer wavelength, but as we'll see, with only the emittance multiplier, the model actually fits this data pretty well over the absorption edge down to around 600 nanometer wavelength. The other data source for model testing is atomic force microscope surface data. This data for Ebner diffuse gold was taken with the K-Sant AFM in the AFRL RDS O-cell lab. The scan area is limited to 80 by 80 microns. It's actually 50 by 50 microns in this case, which means low frequency surface components may be undersampled. But for this texture on a flat coupon, low frequencies are negligible. The surface parameters used by the coherence model are listed in the table. The roughness sigma and the first two derivatives of the surface autocorrelation function rho sub 1 and rho sub 2, which are extracted from a polynomial fit to the computed surface autocorrelation. Higher derivatives are also extracted. Rho sub 3 is listed to ensure they are small compared to rho sub 1 or rho sub 2, consistent with the autocorrelation series expansion inherent in the coherence model. There is variation among different scans on the same coupon, and we would like more AFM data to define error bars on this texture. But this is generally a well-behaved texture in that low frequencies and higher order derivatives are small. At this stage, these parameters can be used as seed parameters for an optimization routine to achieve optimal fits to measured BRDF data. In fact, the surface parameters in this yellow column at the right are used exactly as listed to achieve all of the fits shown in the briefing. So this provides a verified set of surface parameters for Epner diffuse gold. The model can be compared with data within its range of validity. So again, since the coherence model is only a scalar model at this stage, it is compared only with SS polarized radiometry. At this stage, the model assumes perfect conductors, although the fits to diffuse gold at 600 nanometer wavelength imply that this may not be a firm requirement. The model also does not yet incorporate shadowing, which occurs at bistatic angles for deep surface roughness like that of Epner diffuse gold. Shadowing is avoided at monostatic and small bistatic angles, so with the snowball scatterometer we use the 10-degree bistatic configuration drawn here. The first snowball data point is at angle of incidence equals 10 degrees and scatter angle equals 0 relative to the surface normal. Then AOI equals 5 degrees and scatter angle equals 5 degrees in the specular direction, then AOI equals 0, and so on. To extract 1D data, we produce the appropriate grid of full hemisphere solutions. Here the grid covers the wavelengths and AOI sampled in the snowball data. Recall the full hemisphere models are needed for 2D convolutions to describe diffuse illumination, so there's no way around generating the full hemisphere solutions. To extract a 1D data set, we extract one point from each full hemisphere solution. That is the point where the receiver is located. Zooming in on these three AOI solutions at a single wavelength, the snowball 10-degree bistatic configuration is extracted as follows. These vertical lines mark 0-degree scattering angle relative to the surface normal. The first snowball data point is at 10-degree AOI and scatter angle theta sub s equals 0. At 5-degree AOI, the scattering angle is also 5 degrees and is in the specular direction. At AOI equals 0, the scatter angle is at 10 degrees. Then as the AOI increases on the opposite side of the receiver, the scatter angle increases on the opposite side of the specular peak. Back to AOI equals 5 degrees, now theta sub s equals 15 degrees, AOI equals 10 degrees, theta sub s equals 20 degrees, and so on. This is a standard extraction and rendering routine for the coherence model. In order to implement this rendering routine, the model must obviously compute the hemispherical BRDFs quickly. Applying this extraction routine over the entire snowball grid leads to good fits over the range 800 to 1800 nanometers. Keep in mind this fit over the entire band was achieved without changing the model surface parameters from those used to fit the laser BRDF at 1064 nanometer wavelength. Optimization of the surface parameters over the entire band can further improve the fit. These are spectral slices at individual wavelengths using a broadband normalization routine. At this stage, again, there's been no optimization beyond the initial fit to laser monostatic BRDF at 1064 nanometers using the limited raw AFM surface parameters. The fit at 600 nanometers, where gold reflectivity is down around 90%, is even pretty good pending optimization. In fact, the fit at 400 nanometers not shown is even promising. Here are the snowball and coherence models side by side, and the square difference surface to be minimized in an optimization routine. We haven't gotten to optimize over the entire band yet. Finally, we can apply the coherence model to investigate the spectral invariance of this reflector. This surface is used as an IR calibration standard because the shape of the BRDF is constant with the wavelength, which is a stronger condition than constant total reflectivity. If we look at the wavelength dependence of the coherence model for this surface for a simple monostatic geometry, there are three factors alone that exhibit wavelength dependence: a positive exponential, a harmonic function, and a complementary error function. For these factors to cancel each other's wavelength dependence takes a very particular set of surface parameters, that is, a very particular texture. This shows that the coherence model has a detailed wavelength dependence that happens to be flat for this texture over this waveband. We could design surfaces with spectral invariance. These are the three surface parameters to vary in the current model, and the animation shows the different surface against the snowball data as a single parameter rho sub 2 varies. By this approach, we could derive spectrally invariant textures, possibly even more invariant than Epner diffuse gold. In conclusion, the coherence model has been verified pending further optimization versus measured spectral BRDF data of Epner diffuse gold over the wavelength range 600 to 1800 nanometers. AFM surface parameters are used to seed the optimization routine. Coherence theory indicates a non-geometrical convolution to describe diffuse illumination, and full hemisphere solutions are always required to model diffuse illumination. And the model can quantify spectral invariant textures similar to Epner diffuse gold. Our future work will optimize and extend the fits to longer wavelengths, collect additional AFM data, define error bars on model predictions, and extend the model to additional metals, non-conductors, and other geometries. Thanks to these supporters.